Hi everyone. So welcome to this supplementary video. This video is on sort of one of the example problems of modified Bernoulli's equation. So we have discussed this a little bit before, but I just wanted to kind of give an example where we do have a modified Bernoulli's equation. So what you see on the screen is essentially a system where um, we are applying a pressure through sort of this pump here. Uh, which is sort of taking in a fluid and then throwing it up with some height h. Okay, so there's some inlet pressure, some inlet area, some mass flow rate, m dot n, and what we've been asked to find is how much power do I need to put in. So I've been asked to find the power, so power that the pump must add to kind of put the water that high. Okay, so you can imagine if the power of the pump is zero, I will not be able to push the water really to that amount of height. So if the higher the power, the higher the height. However, note that this is something we have not we have discussed, that the mass flow rate, how much amount of water I put to height, should also change power, and that is something we will discuss in this problem. Okay, so how do we do this problem? So this is the problem that we are kind of interested in. So this is what we are saying is our basic equation. Now, a student had asked me, well, we don't define the equation of loss and W. It seems like we are changing it as per our need, and that is correct. So it depends on what you have been asked to find, you should use the equation. So I have three options. If I go to the lecture, one option is to use joules per meter cube, one option is to use meters per second square, and one option is to use meters. You can use either of them and don't get confused. Loss can have either units. Okay, so this is just how the book defines it. You can have loss in both units. And capital WN or small wn have the units of joule per meter cube or joule per kg. Or if you've been given loss in terms of height, you can use HN minus HL, which is H of shaft work in and H of shaft H loss. Okay, so in this problem, I'm choosing to use this top one, and you can use any of the ones you would like, but I'm choosing to use WN. However, that will only give me joule per meter cube. And what I'm really I'm looking to find out essentially is watts, right? So I will get W in the units of joule per meter cube. And if I want to find the power, so right, so let's call it PW power, right? Then I will say should be W in times flow rate, right? Q in, because meter cube per second will give me joule per second. So this will be joule per meter cube into meter cube per second. So this will be joule per second or watts. Okay. So first I will find this and then I'll multiply by Qn. Now you don't have to necessarily do this. You can say I want to use the other one. I want to find the equation in this form, joule per kg. And if you do find in terms of joule per kg, then you can take small wn. As you can see, you can take small wn is the units of joule per kg. And in that case, you will say I'll multiply with the mass flow rate, m dot n. Okay, m dot n. And then in that case, it will become joule per kg into kg per second. And then you will get watt. And what is this mass flow rate? Mass flow rate is simply nothing but Qn times density, right? So that is basically Qn times density. So just be aware of these units so that when you're doing the sort of any problem, you are clear. Okay. In a homework problem, we give you a loss instead of something shaft work in, and that loss is given to you in terms of in terms of meter square per second square unit or feet per second square. And if that is the case, then you are essentially in this sort of space. If you're given you the loss in terms of meter, then you will use this one. If you have given a loss in terms of this, then you will use this one. For the shaft work in, also the same point. Whichever unit we give, you can choose. Here I chose this one because then I can multiply with flow rate, or you can choose a small w in and multiply with mass flow rate. All of them are self-consistent. All right. So let's do this problem. I want to clarify one thing. This is pressure P in here that has been given to you is essentially excess pressure of PATM, excess than PATM. So that pressure already includes atmospheric pressure. So that's why for the purpose of this problem, just because the way book does it, we'll sort of not worry about atmospheric pressure because it will get cancelled from both sides, but I'll clarify this as I go along. Okay, and this is excess than PATM. All right, so my point number one is that the inlet, this makes sense, is that the inlet, and point number two is at the top. Okay, it's the highest point in the system. So I'll choose this to be z equal to zero, z equal to zero just for simplicity. So my z in is equal to zero, and z out is equal to h. Okay, so this is z out is equal to h. So now I start using the formula. And by the way, let's read the problem. The problem says the head losses are negligibly small. So there is no loss in the system. So loss is equal to zero. Okay, just want to clarify that. Let's start. So we have P in. So P in has been given to us as P in plus P ATM. Okay. So this was the excess one. So this was the excess pressure given to us. This is what is at the inlet. Then we have some flow rate, because some flow rate has been given to us mass flow rate. So rho V in square by 2 plus gamma times 0. Z in has been given to us 0 plus W in is equal to P out. And now P out is where we are at the highest height, where there is no velocity. That's the highest height it takes up. So velocity goes to 0, height is h, and the pressure is it's open to air. So it is atmospheric. So P atmospheric plus rho into 0, because it has sort of stopped, and then gamma times h, right? So this goes away. PATM goes away. PATM goes away. This goes away. And so Wn essentially becomes gamma h minus Pn minus rho V n square by 2. Okay. So rho V n square by 2. But to find the power, and power is, I'm defining it as PW, so this power, don't get confused with pressure, is Wn times Q. And so that is gamma h minus Pn minus rho V n square by 2 times Q. Okay. So that's essentially what we have to kind of plug in and find the power for. But just to sort of go a little bit further, note that here Pn has been given to us as 4 psi, I believe. So 10 psi, sorry. So 10 psi. So 10 psi. In this specific weight, you will have to find for, in whatever units, maybe just convert everything to SI. Height is 60 feet, right? So this is given to 60 feet. Is for book, 1000 kg per meter cube. Actually, it's also multiplied with meter square by second, rho g. So it'll be something like 10 to the 4 kg per meter cube. So kg per meter square second square. Okay. And then this one here, rho is again 1000 kg per meter cube. And the velocity is actually not given to us here. It's just given to like a 1.5 feet cube per second, but I've been given a diameter of the pipe, which is 4 inch. So I can find V in from Q pi d square by 4. Q has been given to be 1.5 feet cube per second, I believe. 1.5 feet cube per second. D is 4 inches. And Q is also again 1.5 feet cube. That's it. Okay. 1.5. So in this way, essentially, we have been able to find all the different terms, and we can then get the power in terms of watts, right? So that's essentially the whole idea behind this problem, is that first we have to find the shaft work in joule per meter cube. Then we have to multiply it with meter cube per second with the flow rate to get watts. I just wanted to show you that you can numerically plug in the numbers. It's a problem from the book to get to the power, and then you can find the final answer. Okay, let's just quickly recap what we discussed. We discussed that we have a pump which is trying to push this up, push the water up, and we have been asked to find how much work am I putting in, or how much power I need to push it to 60 feet, and we found the formula. Now I just want to make one point. Look at the formula. See, if I do add, if I make the velocity, if I make the Q to be higher, the higher the Q, the higher is my power, right? The more power do I need, right? So that's how you can kind of think about And if I am essentially like keeping the same flow rate and decreasing the pipe diameter because my kinetic energy is really high, so that's why sort of I will sort of start to decrease some of the requirements for the power. So you have different sort of kind of balances going on in the system. Initial pressure will also help you sort of reduce the power requirement. And the higher height you want to go, gamma h is a positive number. The higher height you want to go, you need more power. So the formula makes a lot of sense. And you just have to plug in the numbers to find the answer. All right. I hope this video was helpful, and this will help you with homework 5, problem 3. And if there are any questions, feel free to let us know. All right. See you in the next video.